Right, so let's start looking at the physics of fluid on the small scale, on the micro scale. And this slide is a little bit of an overview of some of the effects that happen when you go downscaling. Let us just consider a cube with size d and downscale it to a much smaller size. Now if you downscale a cube, actually you scale three things. You scale, of course, the length, d. You also scale down the area. The area scales with d square. So the length scales with d, the area scales with d square, and the volume of the cube will scale with d to the power 3. What are some of these immediate effects of that? Well, the volume goes down. That means also the mass of things go down with the scale 3. That means that all forces related to mass, such as, for example, inertia, gravity, they become typically negligible or very small. And they do that very fast. You go 10 times smaller, 10 times down in scale. That means you get 1,000 times less mass to move. In terms of area, you go down quadratically. And a small area as such maybe doesn't do a lot, but it becomes interesting if you compare area to volume. Because if you scale down the scale d here, for example, with the scale 10, then your area becomes 100 times smaller, but your volume becomes 1,000 times smaller. So if I look at the area per volume, 100 over 1,000, actually I see that the relative area, if you compare the area to the volume, then you see that that one increases. So the surface per volume will increase 10 times, every 10 times I scale down. That means that area-related effects, if you compare area-related effects over volume-related effects, area-related effects start becoming dominant. And if we look at now just the length scale, d goes down. Actually, what that means is that every place is going to be close to a surface. So if I make a channel 10 times smaller, like in this cube, the point that is most far away from the surface would be the center point. And of course, the smaller the cube is, the closer this point becomes to a surface. So if you downscale systems, every point in the system becomes somehow close to a surface and therefore becomes prone to surface-based effects. Let's have a look at some of the physical effects. So mass goes down, inertia goes down, so gravity becomes negligible. Inertial effects go down, and surface effects go also down, but less fast. That means that the flow will be laminar, and that's what we're going to talk in the next couple of slides, so keep that in mind. Another effect is that surface going down, surface per volume going down, the surface-based effect dominates, especially compared to volume based effects. And length going down means that also that actually that diffusion becomes dominant, because now it becomes very, I mean, if the length scale of the system is the same as a typical diffusive length, then diffusion will make that diffusive transport will become a very important transport mechanism. And last but not least, large field gradients become possible. And that is already what I explained before. So if, for example, I put a temperature gradient over these two of 100 degrees and I scale it down 10 times, then my gradient becomes 10 times larger. The first effect we're going to talk about is laminar flow and the difference between laminar flow and turbulent flow. The first thing what we're going to do is watch this YouTube video, and then I'm going to recapitulate what's been said in the video.